In the second part of this lecture, we'll spend some time looking a little more closely at electrolytic cells in the process of electrolysis, and also talk about some applications of electrolytic cells. Now, a direct comparison of a voltaic cell and an electrolytic cell can be found in the figures below, each of which involves a familiar redox system. So on the left-hand side of this figure, we'll try to draw a picture of a zinc-copper voltaic cell where there's, of course, a spontaneous redox reaction that produces electrical energy. And that redox reaction, which I continue to say we've over-talked about, but it's a great reaction to use as an example, is where zinc metal is oxidized by copper 2+ ions to produce zinc ions in copper metal, and excuse me, this reaction is spontaneous by plus 1.1 volts. That's why we can use it in the voltaic cell. Now, if we turn this reaction around and we decide we wanted to push it backwards, this would then be a zinc-copper electrolytic cell. So what we would be doing is using electrical energy to push a redox reaction in the non-spontaneous direction. And although this reaction looks identical to the one on the left, really what we've done here is we've flipped it around. So you'll notice that we've taken the reaction on the left that was spontaneous and we're pushing it backwards. So we have zinc ion oxidizing copper metal to produce zinc metal and copper ion. And since this is the exact opposite of the reaction that's spontaneous, we know this one is not spontaneous. It has a potential of minus 1.10 volts. So here's a figure on the left, which is an attempt to show how we might build this zinc-copper voltaic cell. And you can see that we have a beaker on the left that has a 1 molar solution of zinc sulfate. The important part here is it's 1 molar zinc ion. We have a zinc electrode. We have a salt bridge. We find that what happens spontaneously is that the electrons tend to leave the zinc electrode, producing zinc ions. That's one of the products. The electrons flow spontaneously across to the copper electrode and end up reducing copper ion, which is in the solution on the right-hand side, to copper metal. So the products are copper metal and zinc ion. The oxidation, of course, is what's occurring in the left-hand beaker, and that would be the anode, and that would be zinc going to zinc 2+ plus 2 electrons. Again, the electrons flow through the circuit, show a potential of plus 1.1 volts on the voltmeter, and reduction then occurs in the right-hand beaker, which we've labeled the cathode, and that's where copper ions are reduced to copper metal. We've now put the signs of the electrodes on here. So the anode in a voltaic cell would be the negative electrode, and the cathode would be the positive electrode, which makes some sense because the electrons would be flowing away from the negative electrode and toward the positive electrode. On the right-hand side now we have a figure which is supposed to show the zinc-copper electrolytic cell. You'll notice that the beakers are still in the same place. We have the same solutions, 1 molar zinc sulfate on the left, 1 molar copper sulfate on the right. We still have a zinc electrode on the left, a copper electrode on the right. But what's going on here is that we've decided that we want the reaction to go in the non-spontaneous direction. Now, the only way we can do this is to force it to go in the non-spontaneous direction. You'll notice that electrons are now flowing in the opposite direction. And to do that, we'd have to hook this to a power source that gave us a voltage greater than 1.1 volts. And the reason is because the reverse reaction to the reaction that's going on in the voltaic cell, which we've written here, is non-spontaneous by 1.1 volts. So if we want to drive this reaction, which is again the reverse reaction of the one we started with in the voltaic cell, we're going to have to overcome that 1.1 volt deficit. So we'll have to put more than a potential of greater than 1.1 volts to drive it backwards. So in this case, the anode, where oxidation is occurring, is actually in the right-hand beaker. And in this reaction, since we're driving it this way by hooking this up to a power source, we have copper going to copper 2+ plus 2 electrons. The electrons are forced through the circuit down into the zinc electrode. And now the zinc electrode in this left-hand beaker are the cathode, because that's where reduction is occurring. And we'd actually be reducing zinc ions to zinc metal. Now, as far as the signs on the electrode, since we're driving electrons into the zinc electrode, it's the negative electrode. And we're pulling electrons away from the copper electrode. So this, in this case, would be the positive electrode. So just from the electrostatics here, you can see this takes work. We're pulling electrons away from a positive and toward a negative. Really what's going on here is the power source is putting these potentials on these electrodes, positive here, negative here. Well, a few notes about these two systems here, the voltaic and the electrolytic cells. And some of these things we've already mentioned. In both types of cells, the anode is where the oxidation reaction occurs, and the cathode is where the reduction reaction occurs. That's always true whether it's a voltaic or an electrolytic cell. In the voltaic cell, the anode is the negative electrode and the cathode is positive, whereas in the electrolytic cell, the anode is positive and the cathode is negative. In the voltaic cell, the zinc electrode loses mass as the cell runs, while the copper electrode gains mass. And that makes sense because you're turning zinc metal into zinc ions and copper ions into copper metal in the voltaic cell. However, the opposite occurs in the electrolytic cell. You're removing electrons from the copper electrode. So the copper electrode is slowly turning into copper ions and is losing mass. And the zinc electrode is gaining mass because you're forcing zinc ions to plate out as zinc metal on top of the zinc electrode. Well, here's an interesting question. When Frankenstein was still on the table with wires attached to the electrode on his neck to attempt to bring him alive, was the cathode the positive or the negative electrode? We'll let you think about that. Well, here's an example question that pertains to some information we could get from an electrolytic cell. So what I've done is I've brought the diagram of the electrolytic cell from the previous slide. And of course, this is set up in electrolysis mode. And that means that the reaction that we're driving here is the oxidation of copper to copper 2+, because we're removing electrons from the copper electrode, and the reduction of zinc ions to zinc because we're forcing electrodes into the zinc, or forcing electrons into the zinc electrode. Well, let's suppose the mass of the copper electrode was 25 grams before the electrolysis started. What would be the total mass of this copper electrode if 3.05 amps of current flowed for 17 minutes through this circuit before the power source was disconnected? Now we expect remember, the copper electrode to decrease in mass, because when we connect this to a power source and run this as an electrolytic cell, copper metals oxidize to copper 2+ ions. So we'd expect copper to lose mass. So we're trying to figure out what the mass of copper will be after this much current flows for 17 minutes. Well, we're going to look at this reaction, I should say, look at the solution in steps. And then at the end, we'll try to do it all in one step. So the first thing that we're going to do is figure out what's the total charge that flows through the system if 3.05 amps flows for 17 minutes. So what I've done here is I've taken 17 minutes and converted to seconds, and then multiplied by 3.05 coulombs per second. Remember, amps are coulombs per second. Current is the rate of charge flow, which leaves us with 3.11 times 10 to the third coulombs of charge that's passed through the system in 17 minutes. Well, now we'll take that charge and we'll multiply it by the fact that we know that 1 mole of electrons has a charge of 96,485 coulombs. And what we now know is that in that 17 minutes, there was 0.0322 moles of electrons that flowed through the circuit. Now this is important, counting these electrons, because when we count the electrons, we can get a handle on how many copper atoms were turned into copper ions, because it takes 2 moles of electrons to be lost to produce 2 moles of copper ion, or in other words, to lose 1 mole of copper metal. So right here we'll take 0.0322 moles of electrons that pass through the circuit. We'll multiply by the fact that we'll lose 1 mole of copper metal for every 2 moles of electrons that flow through the circuit. Again, because of the equation for copper going to copper ion that involves 2 electrons. We find out if we do that we actually lose 0.0161 moles of copper from those electrons passing through the circuit. Well, the 0.0161 moles of copper can be converted to a mass of copper using the molar mass, and we find out that 1.02 grams of copper was lost when 3.05 amps of current flows for 17 minutes. So the copper electrode is now 1.02 grams lighter than it was before we started the electrolysis. We could have done this all in one long string by realizing that we can convert minutes to seconds, then we can take the number of seconds times the current to get the number of coulombs, change the number of coulombs to the number of moles of electrons, realize that you produce 1 mole of copper for every 2 moles of electrons that flow, times the fact that we know that 1 mole of copper weighs 63.546 grams. Finally, what's really important here is figuring out what the final mass of the copper electrode would be. And of course, if you start out at 25 and lose about 1 gram, the copper electrode, after that 17 minutes, will weigh 24 grams. Well, let's talk about a commercial application of electrolysis, and this involves the production of aluminum metal. Now, aluminum metal is produced by a large-scale commercial process called the Hall-Héroult process. It uses aluminum oxide as a starting material. The aluminum oxide is obtained from the mineral bauxite. The electrolytic production of aluminum requires an incredibly large amount of electrical energy. That's why it is much less energy intensive to recycle aluminum metal than to create new aluminum metal. Now, unlike previous examples, this redox reaction is not carried out in aqueous solution. Rather, it's done in rather brutal conditions. High temperature melt, about 1,000 degrees Celsius melt, consisting of a mixture of aluminum oxide and a mineral called cryolite, which is a compound of sodium, aluminum, and fluoride. Now, there's several ways that the reactions that take place in this electrolytic cell can be written. What I'm going to show you here is one way of showing the balanced half reactions, which could be accused of being oversimplified. The oxidation half reaction, which of course would occur at the anode, can be written as carbon atoms interacting with oxide ions in a melt to produce carbon dioxide and 12 electrons. Now at the cathode, the reduction half reaction can be written as 12 electrons interacting with 4 aluminum 3+ ions to produce 4 aluminum atoms in the liquid state, because this is a high temperature melt. The overall reaction can be written as carbon and oxides dissolved in this liquid melt plus aluminum ions producing carbon dioxide and aluminum metal. You might note here that it takes 12 moles of electrons to produce 4 moles of aluminum metal. This of course means 3 moles of electrons per aluminum, and also that aluminum metal is produced in the liquid form. Now, one way to draw a schematic for how this might happen in a large electrolytic cell on an industrial scale is this picture right here, and we'll label some things. The cylinders here, gray cylinders, are carbon rods that serve as anodes, or the positive electrode. The CO2 bubbles that are formed on the anode surface are shown here as little white spheres. The hot aluminum oxide cryolite melt that's kept at 1,000 degrees is this brown area here that the electrodes are, the anodes are suspended in. The outside of this is a steel tank that's lined with carbon, and the carbon here, this darker area, serves as the cathode. And you might note here that both the anode and the cathode are made of carbon. However, the carbon anode is consumed in the electrolysis. We can see up here at the anode there's carbon being turned into carbon dioxide, while the carbon cathode, which doesn't appear in the reduction half reaction at the cathode, simply serves as a conduit for electrons. And the aluminum metal that's formed, the molten aluminum metal, is is more dense than the cryolite, so it goes to the bottom of the tank and can be siphoned off as liquid aluminum. And of course, we need the connections for supplying electrical energy from the local power grid. Some things about this cell: aluminum oxide must be constantly added to the melt. The carbon rods serving as the anodes must be periodically replaced as they are consumed in this process. Again, at the anode, you can see carbon being turned into carbon dioxide. And remember, all this is occurring at a temperature of about 1,000 degrees. Well, let's answer an example question involving this aluminum metal production by electrolysis. And here's a question about that process. It says, calculate the number of coulombs of electrical charge required to produce a kilogram of aluminum metal. That would be a little over 2 pounds of aluminum. How many coulombs of electrical charge would be needed? Now, as with the previous electrolysis question, we'll try this one line at a time. So what I'm going to do here is take our kilogram of aluminum and change it into grams. And then I'm going to change the grams of aluminum into moles of aluminum. And so what we have here is the number of moles of aluminum we wish to produce. 1 kilogram would be 37.06 moles of aluminum. Well, how many electrons do we need for that? Well, 3.076 moles of aluminum, that requires 3 moles of electrons per mole of aluminum, would mean that we need 111.2 moles of electrons. Well, we can convert that number of moles of electrons to coulombs by using Faraday's constant. And here we have the fact that we need 1.07 times 10 to the 7th coulombs to produce 1 kilogram of aluminum metal. If we solve this all in one long string, we could do that by converting kilograms to grams, grams to moles, 3 moles of electrons per mole of aluminum, and then converting the 3 moles, or the total number of moles of electrons, to coulombs using Faraday's constant. Now this number of coulombs here probably looks like a very uninteresting number, hard to relate to. I'll tell you right off the bat, that's a large number of coulombs, but let's try to put this in context. Suppose we needed to produce the 1 kilogram of aluminum metal in 60 seconds. Now, if you're going to produce aluminum on the industrial scale, it doesn't seem like a real, too much to ask to produce it in about a minute. So let's calculate the current in amps required to do that. Well, remember, current, amps, is simply the charge required divided by the time it takes to deliver that charge. It's coulombs divided by time in seconds. So I'm going to take the 1.07 times 10 to the 7th coulombs that are required, divide it by 60 seconds and get coulombs per second. And the answer here would be 1.8 times 10 to the 5th, or 1.8 times 10 to the 5th amps. Again, maybe that number doesn't mean anything to you. That's an incredibly high amperage, incredibly high current. So you might ask again, well, is this a large current requirement? I'm telling you it is, but let's do a little calculation here. A typical 1000 watt microwave uses about 9 amps of current when running on high. You would need to run this microwave continually for about 14 days without ever turning it off to deliver enough electrons to produce 1 kilogram of aluminum. So again, you'd have to run your 1000 watt microwave on high for 14 days straight without ever turning it off to move enough electrons to produce 1 kilogram, which is a little over 2 pounds of aluminum. So if you think of the mass of aluminum needed in the world, not just to produce soda cans, but for construction needs and aircraft needs, you can see that the amount of electricity that's required is massive to produce aluminum metal. So the lesson here, of course, is recycle aluminum wherever possible.